Good morning and welcome to Tech 293 for Thursday, January 28th. In this video, we're going to move beyond materials science and we're going to start talking about testing of mechanical properties. And the first mechanical property that we're going to test is hardness. The reason we test hardness first in this class is because, quite simply, it's pretty easy. It's pretty simple. Especially with the machine that we're going to use in Lab 3 to test hardness. It's called an automatic Rockwell hardness testing machine, and it's super easy to use. We'll talk through this in more detail, but basically what you have to do to the machine is make sure the machine is set to the right scale, make sure you have the right indenter installed in the machine. We'll talk more about what that means in a little bit. Make sure you have the right indenter installed in the machine, and then use the arrows on the machine to lower the indenter down just above the surface of the specimen that you're testing, and then press start, wait 10 to 15 seconds, and then read the number that it spits out on the screen. It's super easy. It's really easy. But I do want you to know a little more details about the process of what it's doing. So it is following a process in those 10 to 15 seconds that you're waiting. And I want you to know how it comes up with that number. So we'll talk more about that today. Also, let's go ahead and take a look at the schedule. Today is January 28th, and there is nothing that is due today or assigned today, so that's kind of nice. But I do want to point out that Lab 2 Springs Lab report is due next class on February 2nd at 11:55 p.m. The other thing to note about February 2nd is that that is the date of our first in-person lab number 3. So I will send an email out with the lab groups as well as the time slot that you should come into the lab to do Lab 3. For obvious reasons, with COVID-19, we can't have everyone in the lab or the classroom at the same time. That's why we're having a different format for this class. And so what we're going to do is each lab group is going to come into the lab at a different time. All of the time slots will be during the assigned class time between 2 and 4 p.m. But Lab 3 really won't take very long. It'll probably take each group 10, maybe 15 minutes. So I will make time slots so that each group has adequate time in the lab to do Lab 3. If we look ahead a little bit further on the schedule to February 9th, we see that that is the day of the first exam. So you already have about 75 to 80%, I'd estimate, of the material that's going to be on exam 1. It's going to cover everything in the class that we've talked about up to that point, including hardness testing that we're going to talk about today and do in Lab 3. So you can already begin preparing for exam 1 because you have the majority of the material that's going to be covered on exam 1. All right, so that's about it for the schedule for right now. In today's class, I'm going to make 2 videos. In this first video, we're going to talk in a little bit of detail about hardness testing and what it is and the different scales that we use and how we do it. And then in the second video, I'm going to talk through the instructions for Lab 3 so that we know what we're doing when we come into the lab on February 2nd to do Lab 3. So let's go ahead and get started. All right, so we're going to talk about hardness testing today. All right, so I want you to know the definition of hardness. It's pretty straightforward. It's the resistance of a material to permanent indentation. And that permanent is a key thing. So what kind of deformation do you think we're going to be talking about? Elastic or plastic? You should already have a pretty good clue for what we're looking at. And then indentation just means a mark, you know, a scratch or something like that that would be on the surface of the material. So if I had I'm looking for something to talk about. So if I had a specimen, this is a plastic specimen that happened to be on my desk. I think I gave this example before, but I kind of imagine like trying to press my fingernail into this material. And if I can press my fingernail into this material, and if I can leave an indentation, or if I can scratch it, then it's probably not a very hard material. If I can't, then it's at least moderately hard. So that's not a very scientifically rigorous test. So we are going to have much better tests to measure the hardness of the material. And the next question you should probably ask is, why do we care about the hardness of a material? So there's a couple of reasons. First of all, maybe think about your car. You don't want your car body, the hood or the doors of your car. You don't want them to be constantly getting indented, and you don't want the surface to be constantly scratched, right? So number one, it just looks bad to have materials that are being indented and scratched easily. But also mechanically, every time you scratch something, you introduce a way for corrosion to begin on that material. You induce stress concentrators, which we'll talk about later. But both mechanically and cosmetically, it's usually not a good thing to have a bunch of indentation and a bunch of scratches on your material, your specimen. The other thing is it's actually a pretty good indicator for a material's resistance to wear. All right, so if you've got, say, a bearing, that's maybe a good example. If you've got a bearing and you've got a drive shaft that's going through that bearing, and that drive shaft is going to rotate inside that bearing, let's say it's on a vehicle, it's going to rotate millions of times, and it's got to last a long time. You don't want to replace the bearings on your crankshaft or drive shaft every year or two, right? So you need the bearing and the drive shaft to last a long time. And so they have moving parts. The bearings have moving rollers or balls, depending on what kind of bearing it is. If it's a roller bearing, it has cylindrical rollers inside of it. If it's a ball bearing, it has spheres of metal inside of it. And they are rotating around inside this bearing, and you want them to last a long time. And so what you are going to want is you want those materials that the bearing is made out of, you want them to be made of a hard material. Because if you're going to want it to last a long time, then you're not going to want it to wear out. And the way you make sure something doesn't wear out too quickly is to make it out of a pretty hard material. Hardness is not really defined very precisely. And what I mean by that is I can't really give you the properties of a specimen and say, all right, we got steel, and I tell you it's a BCC lattice structure, and it's got 0.5% carbon. You can't, there's no equation that you can plug into to figure out what the hardness is. So what I mean by that is you can't predict very rigorously what the hardness of a material is going to be. You got to test it. And the way you would know what steel with 0.5% carbon, how hard it's going to be, is by experience. And you've done a whole bunch of other hardness tests maybe with similar steels, and so you know what the hardness is going to be. So it's an empirical test. That means experimental. So it's an experimental type of test. However, you can make some estimations, and you can say relative to other materials, this material is going to be harder, this one's going to be softer, based on a lot of what we'd already talked about. We talked about the types of bonds and what types of bonds are strongest and tend to make hard materials, which types of lattice structures tend to make for the strongest and hardest materials. We've talked about grain size, and density has an impact too. Generally, the denser the material, usually, not always, but there's a loose correlation between density and hardness of a material. So it's all determined experimentally, and there are several different tests that we're going to talk about to determine the hardness of the material. And which scale you use depends on the material that you're going to use. I've got a couple different examples of different types of tests here, and we're going to talk through some of them as well. All right, so the hardness is test method dependent. What that means is if you use the Shore A test, you're going to get a different number than if you use the Shore D tests. And you're going to get a different number yet if you use the Rockwell R test or the Brinell test. So each test is going to give you a different number. And so it's really important when you're stating the hardness of a material, you have to say what test you used. That's really important, because if you say something has a hardness of 50, that means nothing. It doesn't mean anything unless you also state what test you used to come up with that number. So these units are really important. So when you're stating the hardness of a material using the Brinell test, the units are going to be capital HB. When you're using the Rockwell test, it's going to be HR something. And that something is the Rockwell scale that you use. And there are a bunch of Rockwell scales, but the most common ones are the B and the C scale. So when you're reporting the Rockwell hardness of a material, you need to state the number and then HRC if it's the Rockwell C scale, or the number and then HRB if it's the Rockwell B scale. The Shore test we'll talk about last. I've got some examples of durometers that we're going to use to measure the Shore hardness of materials. And the Shore test is mostly for softer materials like plastics, including elastomers and rubber type materials. And the two most common Shore scales are Shore A and Shore D. And we'll talk more about that in a little bit. So this is a relative plot of the different hardness scales. So what this can do for you, and you're actually going to come back to this in lab 3. There's a question in lab 3 that you're going to come back and look at this slide in particular. And what it's going to say is, do the values make sense? In other words, you're going to, in lab 3, you're going to do a couple different tests on the same specimen. And you're going to come back to this and say, do those match up? For example, here's Rockwell B and here's Rockwell C. So you can draw these rough correlations and you can say, all right, well, a Rockwell B reading of 100 is equivalent, I'm going to draw a horizontal line over here, is probably roughly equivalent to a Rockwell C reading of, looks like just over 20, maybe 22, 23, something like that. So those readings are equivalent, the same hardness. And you can do the similar thing with, here's the Brinell scale that we'll talk about. Here's the Rockwell B scale. So it looks like a Brinell hardness of 100 is pretty equivalent to a Rockwell B reading of, looks like maybe just over 60, maybe 62, something like that. So you can use this plot to get a rough sense of the equivalencies between the different scales. All right, the first one we're going to talk about is Brinell hardness testing. This one we're not going to do, but I want you to know a little bit about it because it's a useful scale in that you saw from the previous plot, it goes all the way from very soft materials to very hard materials. So it's probably the widest range of useful hardness readings. So what you do in the Brinell hardness testing is you take a steel sphere that is 10 millimeters in diameter, and then you press it into the material, and you need to be able to measure how much force you're applying as you're pressing that steel sphere into the material. So you got to have some force gauge that tells you what force you're applying to the steel sphere. Then after you've pressed it into the material, then you remove the steel sphere, and then there's going to be an indentation, a circular indentation that's left in the material. And what you need to do then is, as precisely as possible, measure the diameter of that indentation that was left by the sphere in that specimen. All right, so then you can plug it into this equation where this is your Brinell hardness. This F is the applied force or load that you applied to that 10 millimeter sphere. And then D is the diameter of the indenter, which is 10 millimeters. And then D sub I is the diameter of the indentation. So you have to be able to pretty accurately measure the force that you're pushing the sphere into the specimen with and the diameter of that indentation, because your accuracy of your reading here depends on your ability to accurately measure these two things. So some advantages: it's pretty easy. It doesn't require a lot of fancy test equipment like some of the others do, and it's pretty straightforward. I was able to explain it to you in about a minute or two, so it's pretty easy. The Rockwell is going to require just a little bit more explanation, so it's a little bit more complicated. But the biggest downside is that you need to be able to measure very precisely the force that you apply and the diameter of that indentation. Okay, Brinell is not uncommon, but it's not really the standard test in industry. The standard test for most metal specimens is one of the Rockwell scales, and the standard test for plastic specimens is usually one of the Shore scales. So we're going to talk about those two next. First, the Rockwell scale. And these are the two basic types of machines that you will see for Rockwell testing. This is the old style of machine. And with this one, you have to perform each of the 5 steps in the testing procedure manually. So you have to know what you're doing to operate one of these, because there's a specific sequence that you have to do these different steps in. Here's a handle to load or unload the parts. Here you can adjust the load or the force. This is the indenter, and then this is the scale that you read the hardness with. So there's a certain procedure of steps that you have to do to apply that force in a certain order. This is the one, and we do have 2 of these. They are both very old, and they're both down in the Woods lab, Turner 169. So you'll see them when we do some work in the Woods lab later on in the semester. We're not really going to use them though, because they're kind of old and you don't really see these in industry as commonly anymore. This is the one that we have. This is almost identical to the one that we have down in the plastics lab. So the one that you're going to be using in lab 3 is basically identical to this one right here. And it's real easy and straightforward, and we'll talk through it a little bit more in the second video. Basically what you have to do is you have to use these buttons. There's some buttons right here and some buttons right here. And you have to make sure that you're telling it which scale you want to use. So you have to tell it whether you're using the Rockwell R scale or the Rockwell B scale or the Rockwell C scale. And we're just going to use B and C in lab 3. That's one thing. Second thing is, you can't see it very well in this picture, but right here, right around here, there's the indenter. And that's the thing that's actually getting pressed into the specimen. And I'll show you, I have some of the indenters right here. I'll show you, maybe it'll focus a little better if I hold this paper up next to it. Here is a indenter for the Rockwell C scale, and this has a little bitty diamond, I'm sure it's a synthetic diamond, on the very tip of it, and so it's pretty sharp and very hard. Diamond is very hard. So that is the indenter that we're going to use for the Rockwell C scale, which is the hardest scale to measure the hardest specimens. Here is the indenter for the Rockwell B, and I don't know if you can see it, but at the tip of this indenter, there is a little ball. It's a 1/16 inch diameter ball, and that is the indenter that is used for the Rockwell B scale. So the Rockwell B scale is used for materials that are not quite as hard as the Rockwell C scale. The other one that's kind of common for Rockwell testing is the R scale. This one's quite a bit bigger. This is a 1/2 inch steel sphere indenter. And this one is usually used for plastics as an alternative to the Shore test, Shore scale. So you got to make sure that you have the right indenter right down here. There's a little thumb screw that you just loosen with your fingers, and then you can take the old indenter out, whatever it is, and then you slide the new indenter up in there, and then you tighten up the thumb screw. It's kind of like putting a drill in a drill press, a drill bit in a drill press, if you've ever done that before. So it's not hard. And then once you got the right indenter in, and once you've told it the right scale to use, then you can use these up and down buttons right here. That's an up and a down button. And what that does is move the indenter head up and down. And so you want to get the indenter head maybe 1/8 to 1/4 of an inch, something like that, above the specimen. That, you know, if here's the indenter, you want to get it to maybe about maybe 1/8 to 1/4 of an inch on top of the specimen. That way, when you press start, it doesn't have to slowly go down for ages and ages and ages. That way, it'll contact the specimen fairly quickly after you press start. So you get the indenter head just a little bit above the specimen you're going to test. And then if everything else is good to go, you press the green button for, it says start, or maybe it says go, probably start on it. And then you wait for, I think probably about 10 seconds, maybe 15 seconds. And then it's going to go through the different steps of the Rockwell procedure that we'll talk about momentarily. And then when it's done, it spits out a number right here. And there's your reading. So when you record it, you got to make sure you record the number and then the scale, like HRB or HRC or HRR, depending on which Rockwell scale you use. All right, so that's most of what we're going to do in Lab 3. All right, so the second video, we'll talk a little bit more about Lab 3. All right, here is the step-by-step procedure for the Rockwell test. And I want you to know this. I want you to know this step by step. It's only 5 steps in the Rockwell testing procedure. And we'll talk through them right now. So here's your specimen. All right. And the first thing that it does is it applies a minor load. And that minor load is equal to 10 kilograms, regardless of which scale you're using, the Rockwell B or the Rockwell C test. It applies a load of 10 kilograms, and that minor load is designed to break through any surface finish. So if you've got like a surface polish or maybe even a surface hardening just on the very outer layer of the specimen, this is designed to break through that outer layer and get into the inner layers of the material. And then what you want to do is you have to dwell. Dwell means pause of a few seconds. So you apply your 10 kilogram minor load and then you pause. And that allows it to break through the surface finish of the specimen. The next step after the first pause, dwell, is that you apply your major load. And the major load depends on which scale you're using. Every scale has a different major load. So each one has a unique major load. But whatever it is, you apply the major load, which is in addition to the minor load, and then you pause. You do another dwell right here. All right, so now it has forced itself farther into the material. And after you apply the major load, you pause. And what that pause is doing is it's allowing time for plastic deformation of the material. So that doesn't happen immediately. So you wait a few seconds for the plastic deformation of the material to occur. Then the next step, what you do is you remove that major load, but you keep the minor load still applied. So you still have that 10 kilogram load here in step 3, and then you allow for a pause. What this pause is doing, it's allowing for what's called elastic recovery of the material. So we've talked about this before, elastic and plastic deformation. First, you get elastic deformation, that's temporary, and then you get plastic deformation, which is permanent, right? And we talked about this in the very first slide of this presentation. What hardness measures is permanent deformation, and that is plastic deformation. So what step 3 is doing in this dwell right here, it's allowing for the elastic deformation to come back, to be recovered, so that all we're going to measure is the plastic deformation. That's called elastic recovery. So that's the purpose of this dwell right here. Then in step 4, what the machine does is record the incremental depth between the initial minor load, that's right here, and the final step with the major load removed. So we only have a minor load applied right here, just like we only had a minor load applied here, but in between we applied and then removed the major load. All right, so this depth right here has had elastic recovery of the specimen, and so now if we measure from here to here, we're only measuring the plastic deformation that was caused by that major load. All right, so we're only measuring the plastic deformation that was caused by the major load. All right, and then step 5, the machine does this. We're converting that increment, D, right here, convert that increment to the Rockwell hardness value, and it gets reported as a number. And you either read that from the digital readout on the automatic tester or from the analog dial readout on the manual machine. All right, a few notes about this. I've said a lot of this stuff. Dwell times, those are pauses, a few seconds long. That initial minor load in the dwell, that's to break through the surface finish, because you're not trying to measure an effect, usually, of the surface treatment of the part. You're trying to measure the material property of the specimen. The hardness is the material property of the specimen. Then the dwell time after the major load, that gives it time to deform plastically. And then the dwell time after the major load is removed is to allow for elastic recovery of the material. And I emphasize here that hardness testing is designed to measure plastic deformation, not elastic deformation. So remember, the minor load was 10 kilograms, and the major load, I said, depends on the scale. And the two most common scales, the two scales that we're going to use, are the Rockwell B and the Rockwell C scale. And they have different major loads, and they have different indenters. The major load for the Rockwell B scale is 100 kilograms, and it uses that 1/16 inch ball indenter that I showed you earlier. And the Rockwell C scale, which is used for the harder materials, uses a major load of 150 kilograms, and it uses the diamond braille point indenter. So it's an artificial diamond, and it comes to a point. There's lots of Rockwell scales. None of these are as common. Well, the A and the D, E, F are not as common as the B and C scales for Rockwell testing. Rockwell R is fairly common for plastics as an alternative to the Shore testing, and it uses that 1/2 inch diameter ball indenter that I showed you earlier. Don't forget your units. All right, so a few considerations that are in the ASTM document for guidance on Rockwell testing. You shouldn't do it. You shouldn't do the testing on materials that are too thin. Generally, you shouldn't really do it on materials that are thinner than about 1/8 of an inch, because if you do, then you're not really testing so much the hardness of the specimen, you're testing the hardness of the support material that's under the specimen. So you don't want to test material that's too thin. You also don't want to test too close to the edge of the material, because that's going to affect the results. And you don't want to do a test too close to a previous indentation from a previous test. Because what happens is when you get plastic deformation, you get something called work hardening. And we'll talk about that later on in the course. But work hardening is exactly what it sounds like. As you plastically deform a material, it gets harder. It actually gets stronger and harder for a certain period of time. So if you test too close to a previous indentation, within 1/4 of an inch of a previous indentation, then your reading is not going to be valid. So stay at least 1/4 of an inch or so away from a previous indentation. And kind of like cutting a cylinder with a bandsaw, it's the same idea. If you're doing a hardness test on a cylindrical object, all right, it's dangerous to cut a cylinder on a bandsaw. You need to be really careful. Same thing with hardness testing, because you got this point that's coming down on this cylinder, and it can be dangerous. You're actually applying quite a bit of force and a very high pressure, because this is a small point. So it's got 100 to 150 kilograms of force on it, depending which indenter and scale you're using. And it's applied to a very small area on the specimen. So it's possible that you could get these things to fly off of the test stand and potentially hurt somebody. So you need to use a proper fixture, and we have one down there, a fixture that has a groove in it that you can put a cylinder inside to hold it in place. And if you're testing it, the specification calls for within 2 degrees of perpendicular. The indenter should be within 2 degrees of perpendicular to the specimen surface. The advantages of Rockwell test: if you're talking to someone in industry about hardness testing, chances are they're thinking of the Rockwell test, because it is the standard hardness test in industry. It's precise, it gives accurate readings directly and very quickly, and it's really easy to learn to operate the testing machine. Even in an old style with a manual procedures, it's still pretty quick and easy to learn. The disadvantages of the Rockwell test: well, it kind of ruins the part. I mean, it doesn't break it, and it's sometimes called non-destructive testing, NDT, but you can't take this part and sell it afterwards, because it's going to leave these indentations. You'll see in lab 3, it's going to leave these little indentations in the specimen. So you can't really turn around and use that part or sell it to a customer. So it may not be destructive, but you can't use the part again. The test machine, you'll see, it's not real portable. I mean, you could, but you probably need at least a couple of people at least to help you move it. It's heavy, and they're relatively expensive. They're about 25 grand a piece for the automatic ones. And you're going to get some experience using the automatic Rockwell test machine in lab 3, but I do kind of lament the fact that you're not going to get experience with the old style of Rockwell hardness testers, the manual style. So I at least want to show you this video about using the old style of Rockwell hardness testers, the manual testers. So I'm going to play this video for you, and it's only about 3.5 minutes, and it'll walk you through all of those steps that we just talked about while using the old manual style of Rockwell hardness testing machine.
The Rockwell hardness test is used to test the hardness of a material by indentation. This machine here is a CV600A, which is a hardness tester, and it's got two scales. It's got the scale C and scale B.
That's C and B.
Scale C uses a diamond indenter like this one. It measures materials like quench steel, tempered steel, more of the harder materials. Whereas the scale B measures aluminium, alloys, copper, malleable cast irons, but that one uses a steel ball indenter. Material like mild steel. This is used as a calibration test piece to check that the machine's in working order and is up to calibration. It's got numbers written on here that specifies its actual hardness. This is mild steel, so we'll be using a scale B indenter with a steel ball. Firstly, you want to put it into the holding chucks and tighten it with the help provided. Okay, next, we want to put the workbench that we'd be putting the specimen onto. These can come in various different shapes because you might have a rod that you want to try and test. So with a B scale indenter, you also first of all you have to apply a minor load and then a major load. The major load has
a minor load, not binary load.
On the side of this machine, and we just make sure that it is reading 980. You have a specification sheet that shows you the loading, the minor and major loadings of different scales. Next, we'll put our test specimen onto the bench and use the feed handle to bring it all the way up to the ball indenter. Find a nice flat spot on the indenter and just let it touch the surface of the test material. By turning this feed handle, we'll apply the minor load by allowing the small needle to touch the red dot. So once that's there, we've applied the minor load. If we're using the B scale indenter, we have to look at the inside reading of the dials. So we want to position the big needle so it hits 0 on the red scale. This machine is hydraulically controlled, so it's got the major load configuration setting here. So once you've applied and calibrated the dials, you can apply the major load by simply just pushing it down. Then you wait for the needle to settle. And release the load. From this specific test that we've done now, we have this material, and it's given us a number on the B scale. That number represents the Rockwell hardness number. It's also very good to do this test 3 to 5 times just to get a good average for the hardness of the material. Thanks for watching.
All right, you can tell those subtitles were automatically generated because they mix some things up, but I still think it's probably useful for you because I don't know how good the audio is carrying over to the microphone. So the subtitles might have been kind of useful for you, but there were a few errors in there. I tried to point out some of them as they were coming across. Maybe the guy's British accent, maybe that was throwing off the subtitles. All right, hopefully that video was kind of helpful and it gave you a demonstration of the manual Rockwell hardness testing machine. Okay, the last scale of hardness testing we're going to talk about today is shore hardness testing. This is usually for considerably softer materials like plastics. It's pretty commonly used for plastics. And one thing I want to emphasize is that shore is the scale. Specifically shore A or shore D are the most common ones. And the device that we use to measure the hardness of something with the shore scale is called a durometer. And I'll show you some pictures of those, and you're going to use these in Lab 3 also. So again, it's for soft materials. The durometer is this handheld device. There are digital ones, but I actually specifically wanted an analog one. I just like them better. So these are a couple, actually we have a couple of different scales of durometers. And the procedure is pretty easy. basically, I don't know if you can see it, but it's got a kind of like a needle, got kind of a needle on the bottom, and it would be the same thing down here at the bottom of that digital durometer. Down here, there would be a needle that obviously you can't see because it's pressed into that specimen. But basically, the procedure is that you take the durometer. And I don't really want to press it real hard because it's sharp. So when you're doing this in Lab 3, I would not recommend that you measure the hardness of your fingers or your fingernails or of your lab group members' fingernails or anything on their body. So don't do that. Only measure the hardness of the specimens that I have provided for you. Basically, you take the durometer and then you press it into the specimen until the plate here is coplanar with the surface. Basically, you press it into the surface until you can't press it anymore into the surface. That's when the flat part of this is resting on the surface of the specimen. And then you just read the dial. And it's kind of nice because these have a, let me actually do one, because I don't think you can see it, but they actually have a little red needle that's going to move with the black needle, and then the red needle is going to stay, so it's easier to read. So here, I'm going to go ahead and do it. Here's a piece of polypropylene. So I'm going to pick a spot that's far away from the edge, and I'm going to press it into the surface as much as I can. All right, and then I'm going to let go. And so you can see how the red needle stayed at the maximum and the black needle went back. So now I can read the red needle, and looks like it's about 67. So this was the Shore D durometer. So the way I would label this is just 67D. That's the way that you label the units for the Shore D scale. All right. All right, so softer materials, plastic, rubber, composites, these are all things that the Shore scale is used for. The type A is a softer scale than type D. So if you've got like a soft rubber material, you probably want to use type A. And if you've got a harder plastic material, then you probably want to use type D. Just like in the same sense that types Rockwell C is a harder scale than Rockwell B, same thing with Shore D is a harder scale than Shore A. And there's the same normal precautions. The specimens really should be about 1/4 inch thick. To be totally honest with you, these are not 1/4 inch thick, so our test specimens are not ideal, but you want to make sure that you don't use specimens that are too thin for the same reason. Otherwise, you're basically testing the hardness of whatever is below the specimen, not the specimen itself. And when you record these, make sure you include units. I really prefer this right here, although technically this is acceptable as well. So this number is whatever your reading was from the test, and then this is the scale, either A or D. All right, and there's some overlap in between the Shore A and the Shore D scales. These are your harder materials over here, and these are your softer materials over here. So there's some overlap in this region right here. So it's possible to convert between hardness scales. I will say that it's usually not recommended. In fact, ASTM cautions against converting between different scales, just because the tests are experimentally determined and they're test dependent. So generally, people do it, but it's not a great idea to convert between hardness scales. But people do it. And the pros and cons of the Shore test, well, as you can see, it was really fast. You just watched me do one test. You're going to do more than one on each specimen. But super fast. I mean, on the order of seconds to do a test, and it's really easy. It requires very little training to do. These are relatively cheap. These were about $100 a piece, maybe a little bit more. But compared to the $25,000 automatic Rockwell hardness testing machine, these are pretty cheap. You can get cheaper ones that are lower quality, and you can get more expensive ones that are probably a little higher quality too, but you can get pretty good durometers for about $100. The disadvantages here are that you can affect the reading by pressing harder on the material. You'll see that in lab 3, but if you press really hard or you don't press enough, then you can affect the overall result. So that's a disadvantage. And another thing is that it's really important that you apply the durometer straight down onto the test specimen. If you apply it at an angle, well, you risk damaging the durometer, first of all, but second of all, it's going to affect the reading as well. All right, the basis for this presentation was the ASTM test procedure, and that's the basis for lab 3 as well. So that's going to wrap things up for this video. In the next video, we'll talk through the instructions for lab 3. That's when you will come into the lab next Tuesday, February 2nd at your assigned time with your lab group. And you'll do some hardness testing, both with the automatic Rockwell hardness testing machine, as well as with the Shore D durometer. So we'll talk through those in the next video, so I'll see you there.